Hello, everybody. I hope you had a good weekend. It's Monday, the 12th of October, 2020. This is Calculus. My name is Scott Grizzard. We are going over quiz 8A. Are there any questions before we begin? Okay, I don't know why this isn't working. So there's several little things that aren't working apparently in Blackboard Collaborate Ultra, but I think I've got them working. Of course, you can watch the stream on Twitch as well. Questions, you can ask them in Blackboard Collaborate Ultra or in Twitch, but please remember questions on Twitch are public. Okay. So, did the audio just cut out on... Okay. So, of course, you need to mute the audio in either Twitch or Blackboard Collaborate Ultra, depending on how you're viewing it. Okay, so let's go ahead and go over this quiz. So, there we go. All right, write the formula for the linearization, which is, of course, the formula I gave you at the end on Thursday. And that is this, right? So it's L. F A. So this is at X of A. I don't know why the writing on this thing has gotten so bad today. Of X. And you didn't need the F8 because the book didn't have it either, but you could have done it or not. This is F of A plus F prime of A times X minus A. How do we feel about that? 1 to 5. Let's see. Share. Pulling multiple choice. Everyone, by the way, has the exact same complaint that there's no way to set these polls up in advance, apparently. And everybody, we have these meetings once a week or so, and everyone's complaining about the same thing. In Teams or in here, you can't set up the polls in advance, apparently. Okay, well, let's look at this definition for a moment. Let's just look at it. So if we let's let A be X naught. All right, and then so if we have an X naught for A, we get that L of X equals F of X naught plus F prime of X naught times X minus X naught. All right, well, we've done that. So let's let F of X naught equal Y naught. And let's say that, okay, so that gives me L of X equals Y naught plus F prime of X naught times X minus X naught. All right, well, let's let Y equal L of X. And then I get Y equals Y naught plus F prime of X naught times X minus X0. All right, well, denote this as, well, this is just the slope of the tangent line then. M at Y, so we'll designate this dy over dx at x equals x naught. And then we get y equals y naught plus dy over dx at x naught. And we'll just call this m. X minus x0, and then let's move this over to the other side just because we can. What is this? What is the linearization? It's the formula for the tangent line written as a function. Okay. Yeah. So that's all the linearization is. It's just you take the tangent line, the point slope formula for the tangent line, and you make a function out of it, right? It's a new function that tells you it's the functional form of the slope of the tangent line. Not the slope of the tangent line, right? 1 to 5, how do we feel about that? Okay. So, is there something new to memorize? Sure. You need to memorize that there's a kind of little bit of new notation. But that's all. This is something you already knew. I made you memorize something you already knew. Aren't I a mean person? Now, we're going to use the linearization as a function to make estimates. So the use of it is a little new, right? We're going to find points on this line, but it's the tangent line. In other words, there was a reason why we're asking you the tangent line again and again and again and again. It's because what you're finding is the linearizations. Okay. Well, let's look at number 2 here. Our over-decorated derivative problem. Let's sketch a tangent line first. So I want the tangent line, the line tangent to the graph at x equals 1. So that's about there. All right. So how do we feel about that 1 to 5? That's where that tangent line is, right? I have to go through x equals, maybe a little bit. Maybe it's a little bit. Maybe it should be a little bit more like that. I mean, I'm not. Yeah, maybe more like that. Something like that. That kind of passes too. I want something that passes. But are we all on board with the fact that that point right there is the point we're looking for? That's the important thing here. That's the point through which this line should pass. There we go. Something like that. Okay. Now I want to compute f prime of x. Now this is a big mess. Okay? But it's doable. So, let's see. Where was I? Sorry, things are like mixing up. Okay, so this is a mess. It's over decorated, right? I've got I want to take the derivative with respect to x of the following. So I've got 1 over 4 x to the 4. So this is going to be 1/4 x to the 4th over 3, that cube root there, with a negative sign in front of it. Plus, this is going to be the derivative of 2/3 x to the 1/3 minus the derivative of 1/2 root 10 to the root 10 plus the derivative of 1/j. All right, these are both constants. Okay, so this is a constant here, and this is a constant here. So when I take the derivatives, they're off by themselves, right? If they were glued to something that was moving, you'd keep them. But they're off there by themselves, and because they're off by themselves, they're both going to go to 0. So what I'm left with is this weird derivative here. Okay, so this is going to be -4/3 times 1/4 Yes. Should actually be to the 3/2. Yes, I messed it up. All right. X to the -4/3 minus 3/3 plus 3/2 times 2/3 times x to the 3/2 minus 2/2 minus 0 plus 0. Okay. So now I'm going to do a little simplification because now my derivative is done here, but it's going to ask me, so right now I'm done. Well, except for the fact that I need to subtract my constants, my exponents. However, this thing, it's asking me if my slope that I get from part B agrees with part A, right? So what I'm going to do is I'm going to simplify this a little to make that calculation a little bit better. All right, you don't have to do this. The third term is 0 because it's 1/2 to the square root of 10. This is a constant. This term is also a constant. Okay, now I'm going to simplify simply because I'm going to want to make that calculation a little bit easier. So -4, this is going to be -7/3 plus the 3 and the 2's are going to cancel. This is going to become x to the 1/2. Okay. And then does my slope agree? So let's see. F prime of 1 equals -1/3 times 1 plus 1 to the 1/2. Well, that's nice. That equals -1/3 plus 1, which equals 2/3. So, yes. All right, because if I look over here, that's basically what I want to do. Yeah, you can, but you need to actually say you kind of get 2/3. Especially if they're not kind of accurate, right? Because this is about, if I go, 1/, I go, kind of almost halfway. You need to do you really need to solve for that 2/3. That's kind of the justification. That's kind of the why or why not thing. All right, how do we feel about this problem 1 to 5? Let's see. Multiple choice. Oops. There we go. So these over-decorated problems here are kind of a popular thing to make you, and I even messed it up, right? I mean, this should have been x to the 2/3. I'm sorry, 3/2. I even messed it up. So if you're messing them up, you might want to do this in more than one step. You might want to put especially when there's square roots, you might actually want to put the thing in here. So these kind of over-decorated things, just make sure you're careful with those. Yeah, I butchered it. Hope you didn't. As I said, these are these annoying. I hate these problems basically. Not the graph setup. I actually think this is a good setup for a problem. I hate these. Right? I hate these kind of over-decorated exponent problems because it's so easy to make a stupid mistake on them, right? The big concept, this is supposed to be a class about big concepts, and they're these nitpicky little problems. Ugh, I hate them, right? There's no big concept associated with this problem. It's just do the power rule properly. By the way, what's J? Did anyone look it up? J is a very important concept. Is a very, very, very important constant here. It's pi squared times 7 to the e minus 1 over e minus 9. All right, which is approximately 867.5309. 80s reference. Just in case you wanted to know. Any questions? All right. All right, let's look at this balloon here. A spherical balloon is inflated at a rate of 2 cubic feet per minute. How quickly is the radius expanding when there's already 4 pi over 3 cubic feet of air in the balloon? All right, so we've got a sphere. And yes, on your test, it must be a perfect circle. Oops. Stop that. All right, so we have a sphere here. It's got a radius that's expanding, right? So there's volume going into the sphere. So R is getting bigger. There's air being pumped in. So the volume's increasing. Okay. And I know that the rate of 2 cubic feet per minute, right? So let's write down our variable list here. We've got, we're going to have this variable and that variable. So we've got V volume. It's being measured in cubic feet. We've got R radius. Let's see. That's going to be in feet because this is in cubic feet. We've got time. Things are happening per minute. So we've got time. It's minutes. This thing is moving. This thing is moving. This thing is driving. We've got dv over dt, and we've got some data on it. 2 cubic feet per minute. We've got, so this is the change in volume. Cubic feet per minute. I already wrote that down. And let's see, we got a radius over thing. This would be change in radius with respect to time. All right, and that's the thing we want. All right, so everything's moving. I don't really have anything that's static. I've got some snapshot data. So snapshot data. So I've got nothing fixed. And then I've got snapshot data of V equals 4 pi over 3 cubic feet. Okay. So how do we feel about this kind of setup here? Trying to figure out everything that's going on. 1 to 5. Let's see. Polling, multiple choice. Question 3 setup. So how do we feel kind of about this setup, right? Nothing's fixed. I've got some snapshot data. I've got some volume moving, radius moving. Time is kind of driving. Okay. I got this relationship here. I've got V equals 4/3 pi r cubed. I don't have any fixed data. Right. I've got nothing fixed, so do not sub in. And then I'm going to take the derivative with respect to time because time's the thing driving this system. Four pi over 3 cubic feet is snapshot data. Okay? So at a particular point in time, right, this right here is snapshot data. Okay. All right, so dv over dt, I'm going to take the derivative here. I'm going to get 4/3 pi r. This 3 is going to come out in front. It's going to be pi r squared dr over dt. All right. And that's going to give me 4 pi r squared dr over dt. How do we feel about that, the derivative 1 to 5? So let's see. Stop. Why does it keep doing that? I hit stop and it I think I'm mashing the wrong thing. It's r squared because I took the derivative of r cubed, right? So this is a chain rule here. So what I actually had was d over dt of 4/3 pi r cubed. And this thing right here is moving. I need to make this so that it's obvious that what I'm doing is on the side here. So let's do that on the side. come on over here to the side. All right, so this is a good question. Why is that the derivative? Okay. So now what I'm going to do is I'm going to apply the constant multiple rule. I'm going to pull out both constants. So this is going to become 4/3 pi times the derivative with respect to t of r cubed. Now, I've got t here and r here, and I can't do that. That's bad. It's bad. Bad. You all are too young to remember Drew Carey doing George H.W. Bush. It's bad. Great Saturday Night Live skits. That was Saturday Night Live when it was good. Okay, so this is baggage now. So I'm going to carry my baggage. Now this is a T and that's an R. So I need to do the chain rule. And what I'm going to get is d over dr of r cubed times d over dt of r. Carry my baggage. Now I can apply the power rule. So now when I apply the power rule, this becomes 3r squared times the derivative of r with respect to t. And then I am going to simplify this because it's going to be in my problem, and I wind up with that. Okay, how do we... So, all right. All right, so now I've got my derivative. Now sub in. Okay, so what I've got, so snapshot. Right, I've got dv over dt. That equals 2 cubic feet per minute. Equals, then I've got 4 pi. I've got an r here, need r. And note this is r when volume equals 4 pi over 3. So this is, I don't know if you've caught on to this notation yet. But if I do this, if I do r and then I do a line down and then I do v equals 4/3 pi. I'm sorry, 4 pi over 3. That's the same thing. Does everyone understand what this notation means? Is everyone on board with that? 1 to 5, how do we feel about that notation? That's very useful notation. It's German, you know, but we shouldn't hold that against them. It's nice Leibniz notation. This kind of win bar notation. Let's see, stop. Yes. Start. So how do we feel about that notation, 1 to 5? This is kind of like the win bar or win line notation. It's actually very useful, especially when we get to integrals. So this is saying r when v equals this. You've seen me use it a couple of times, but I can also do, right, I've also got dv over dt. I want... dr over dt when v equals 4 over 3 pi. Right? So this is the change in r with respect to t when, I know my head's in the way, v equals 4 over 3 pi. All right. So that's what that notation means. So, and it's common notation, especially in physics. It's really common in economics when you have curves that aren't quite functions, because like labor curves, there are things that violate. I love how economists say the law of supply and the law of demand. No, the economists, when they're saying the law of those things, they mean the general rule. Right? Physics has laws that don't get violated. Economics has the tendencies. The law of supply. Shut up. So supply curves for labor tend to bend back on themselves, because when people get rich, they want to kind of enjoy their life a little bit more. So they at a certain wage, they stop working as much because now they've got all this money that they want to go spend. So things like labor supply and labor demand curves tend to be a little wonky at certain places. So that's why the economists love this notation. Anyway, so I need R. I want R when V equals 4 pi over 3. And I'm just going to leave this off. So this is going to be 4 pi r squared times dr over dt, which is what I want when V equals 4 pi over 3. I'm going to stop that. All right, so I need some snapshot data. So now I'm going to find my snapshot data. Okay, so this is all snapshot. So I'm not going to deal with the derivative. Notice I haven't subbed in yet. So I'm going to have V equals pi 4/3 pi r cubed. And I have my V. My V equals what? What's my snapshot data? I've got 4 pi over 3. Wait, what? Of course, this is totally contrived, because it's all set up to work out nicely, right? Well, isn't that nice? The 4/3 and the pi's are going to cancel. And I'm going to be left with 1 equals r cubed, which means r equals 1. How do we feel about that little solving for the snapshot? Stop poll, start poll. So the idea here is that I need another piece of snapshot data. I need my V. So now what I'm going to get is I'm going to get 2 cubic feet per minute equals, let's do this in purple because this is actually the kind of end of it. Yeah, so you solve for R in the snapshot. So the idea is you kind of have two different kind of problems running around, right? You have the thing that's happening while the motion's happening. That's the derivative. So if I push play on the movie, right, while the movie's playing, I've got things that might be fixed. Here I didn't have anything that was fixed for the whole movie, but I might have things that are fixed for the whole movie. Okay? And then I've got some things that are fixed when I hit pause, but only when I hit pause. So as this balloon or the sphere expands, right? And if you want to do this experiment yourself, it's actually kind of cool. You take Freon and stick it in a balloon and leave the balloon. And the balloon, right? Normally we think of balloons shrinking as you leave them, but because Freon is heavier than air, it's denser, the balloon will actually get bigger. It's really cool. If you take something bigger, denser than air, you know, it gets bigger when you fill it up with the balloon. It'll also make your voice go, oh, Bob, right? So when you inhale the helium, you go, you know, but you do the Freon or whatever, it goes, oh, yes. So it's kind of fun. Anyway, this is what happens when, you know, you grow up with science geeks as parents, right? I am not. I'm a math geek. Science stuff. It's fun to me. But anyway, so so that's the thing. I want to, you know, when I want to hit pause on the movie, I need to solve for the pause data, or what I call the snapshot data. Pause data is probably better. And then I need to solve for the play. Okay, so now I got all this data again. We're going to put this in. So we got 2 cubic feet per minute. I wish I had a tape of me diving on Trimex, because it was really funny. Because when you're diving on Trimex, you're inhaling helium, and your voice, if you've got a headset underwater, your voice goes, yeah. They've actually got like helium descramblers that will actively move the thing down if you're talking to surface support. It's fun. So you got pi r. Now this r that I needed was 1. That's convenient. Times dr over dt when r equals 1. And this 1 here is in, the radius is in feet. So this is going to be in feet squared. And that's going to give me, so the 2, I move over to the other side. So that gives me 1 over 2 pi equals dr over dt. And the units match, because the feet squared will cancel with the feet cubed. This will just become a foot. That will be that, feet per minute. So, and then I write my statement, right? The radius is expanding at a rate of 1 over 2 pi feet per minute. Okay. The sentence is one of those things that's a save your ass thing. Right? You don't have to do it, but you might want to, because you have your units there. You have what you set it. What's going on? Well, the thing's expanding, right? As the volume increases. I might even want to add that, as the volume increases. Okay? Again, I just might want to say what I mean. It's a save your ass thing. Right? What if the key had a negative on it? Well, you said what you meant by the 1 over 2 pi. Okay, so how do we feel about that kind of whole problem, 1 to 5? And all of these problems, they're organization heavy, right? I mean, look at this. I spent 15 minutes on this problem? Maybe 10, 15. And it's all, the organization. Of course, I also did, some silly stories and some of this stuff. But it's really in the organization, right? This idea, I need to make sure that the volume is that. So I put my snapshot here. I didn't know what R was in the snapshot, so I had to find it. And it's really, there's kind of a thing. So how are these problems graded? This is a very good question. So the rubric will probably look something like this. And I don't know what the rubric will look like exactly, because I didn't write it this year. Usually they look something like this, right? So I usually have... let's see. It depends on the setup, what they look like, but it's usually like, what is this? How many points is this? Okay, this one's 10 points. So usually this one would be like, there'll be 1 point for units at the end, usually like 3 points, answer, correct, and then, taking the derivative will be 3 points. It's probably 2 points for taking the derivative, 2 points doing the derivative correctly. So this is like 2 points for knowing you had to take a derivative of the thing, and 2 points for doing it right. And then it'll be like 3 points solving the snapshot. I'm actually over this, so it'll probably be 2 for this, 2 for this, right? And it'd probably be 1 point for the right answer, 1 point for the union units, and then 1 point for putting it together. Neatness / put together. Right, and that's the idea, that you could figure out what the heck you were doing without divine intervention. Is that enough points? 6, 7, 8, 9. It might be 2 points for this. There we go. So something like this will be the makeup of it, right? And then you'll have all of these partial credit rubrics. So this is the main rubric. And then you'll have a bunch of partial credits. So you'll have something like partial, max, it'll be something like partial max 4 or half missed. Right, so if you mess up on only 1 point, like if you forget your units, you're not going to get anything back for the partials. Or you might get half a point back for the partials. But the way it'll work is this. It'll be like 1 point each variable maybe, 2 points picture, 2 points labeled picture, with arrows. It'll be all sorts of things like this. Now, usually they're out of 14 points. This one's out of 10. So there's usually like, you get like just under half partial credit, right? And depending on the problem, it depends how much setup you need, right? So some of these are hard in terms of what you need to take the derivative of. This one, it's kind of obvious. I gave you the equation. So you take the derivative of that equation. Right? The motto for this test, when in doubt, take derivatives of everything. All right? That should be the motto for test 2. We'll write that right here. Motto for test 2. When in doubt, take derivatives of everything. Right, just take derivatives. So even if you had totally messed up the pooch, you got a lot of points for taking up the derivative. Then, if you took the correct derivative, let's say you messed up the derivative, you could have secured 2 points for knowing to take a derivative, 1 point for including some kind of units, and then you could have gotten 6 points if you totally foobarred the derivative. You get 2 points for knowing to do a derivative. Right, of that equation. You took a derivative of that equation, or you tried to. You knew you had to do something involving a derivative, right? And then you drew a little picture, you did some labeling. You're going to get a lot of partial credit for that. Okay? The big point, don't let these problems have a lot of bark. Don't leave this problem blank on the test. If there's nothing else you take from this, don't leave this problem blank. Okay? Does everyone feel, you can get, even if you botch the problem, you can get more than half the points. How does everyone, I want to emphasize this, how do we feel about, don't leave the problem blank, basically. 1 to 5. How do we feel about that little piece of advice? So it used to be when we were in-person classes, if you gave me your test early, I would flip through it, and if you left anything blank, I would give you the evil professor stare and make you sit back down and finish the test. I'd be like, just do something. right? And I can't, unfortunately, I can't do that here. You know, if I could give you evil professor still and make you sit back down, you know, you get over this intimidation about the problem. Just don't leave it blank. Whatever you do, don't leave it blank. Draw. Take a derivative of anything, right? You'll get points. You know, if a 14-point problem, 7 points is a lot better than none, right? That's a letter grade and a half. You know, for just doing, no, it's 2/3 of a letter grade, right? For just doing something. The whole problem's a letter grade and a half. 2/3 of that. Do something. Okay. Any other questions about this? Okay. So what I'm trying to get you to do, especially in this test, you've got like a century to do this test. We're actually lobbying for when we go back to in person, we're trying to get 90-minute tests instead of the 75-minute for the future, because it actually has made a huge difference, just having a little bit more time. But yeah, this whole don't leave it blank. Okay. All right, so let's stop the poll here. Let's see, end the poll. Okay. So the problem set, let me talk about the problem set very quickly before I turn off the Twitch so that people can hear it later. So the problem set is all about, let me pull it up. So the problem set this week is all about related rates problems. I have 6 related rate problems on this problem set. Pick 3. 3, 3, 3, 3. You can do all 6. I'll be happy. 3 is what you have to do. Okay? Is everyone on board with this? 3 problems from this problem set for the related rates problem. So question 1 is going to ask you to list your steps. So there was like the steps in the notes, the steps in the book, the steps in the, pick a set of steps and list them. Okay? Then you need to do 3 of these 6 related rate problems. So there's a nice little spreading oil one that I pulled off from a test a year and a half ago, like 3 semesters ago. There's Boyle's Law. This one's in the book. This one was on WebAssign. I think we actually asked it 2 years ago or 5. I've been teaching too long. We've got this one here. This is the one off the peer leading. It was the second problem that you probably didn't get to in peer leading. And it's right here. This one is probably takes too long for the test. But I put it on there. It's a good one to kind of mess with this idea of things that move and things that don't. This one I pulled off an old test. Actually, I think I pulled this one off an old makeup exam. This one's a good one. It's got, I wrote it and I pulled it off a makeup exam. I actually wrote most of these except the ones that were not in the book. I mean, except the ones that were in the book. I wrote most of these. I didn't write this one, obviously. That was in the file. That one's from the book. This one I wrote. This one right here. This is a good one because it's a gas law and it's got a quotient rule instead of a product rule. Now, you can multiply these over, right? This can be P equals CT, but when you take the derivative of that, you're stuck with the C. So you have to solve for the C as data when you do it. It's faster to take the derivative and make that C go away. This one right here is the mechanical winch problem. This is similar to one that's in the book. I think the other leg of the triangle is in the book. This one is hard. This one's on the bootleg, and it is a related rates problem. But this one's hard because you don't see it right away. And then for the last step, after you've done your 3 problems, I want you to rewrite your steps for doing them. Okay? So even if you have the exact same steps, rewrite them. Any questions? Okay, so I'm going to start the groups here. Let me see. All right, so I'm going to stop streaming.